So this is actually about a slide, not exactly the same slide, but the same table, right? We had a table that displaying the age variable. You know that sometime age variable is observed in terms of its actual age, right? And sometimes people actually organize them into a frequency distribution type like this. So assuming that this age actually originally is quantitative, right, but we categorize, right? So it help us to actually to understand the distribution pattern, right? Just by those data value individually, it's probably a little bit hard to actually display the information. So whenever we have quantitative variable, usually we like to somewhat defining these ranges, right, or classes, and then we'd be able to display the data, right? So I use these classes defined, and I count the frequency of occurrence, right, for data lies in the different range, and I convert it to percentage. Then I'll be able to display a histogram that's give me the relative frequency distribution, right? So I can see the shape of the distribution. So this distribution actually is not quite bell-shaped, right? Age distribution for this variable is not bell-shaped, right? So anyway, this is from a data, and like I said, it depends on the size of the data. If I have maybe 200 and 300 pieces, and I draw a distribution in a histogram from the data, and I saw a pattern like this, I feel comfortable that the distribution for the population of this type is probably just like that, right? But if this is from only like 5 or 10 pieces of data, and you draw a chart like this, now that's small sample, about a lot of sampling variability there. So next time when you take a sample of 5 or 10, right, the pattern may not be exactly like this. So really, if you want to see the actual distribution pattern that's closer to real population distribution pattern, you really like to have larger data, right? My experience is at least 100, right? 200, 300 better, right? But only 20 or 30 or 10, right, would be really hard to really see the pattern. Okay. Anyway. What I'd like to do this next hour actually is going through some of the topics in the probability chapters, right, which is something you're going to study in the next couple of weeks. Okay. I think there are some basic concept in probability that I believe most of you are pretty good, right? The basic idea in probability, right? In applying to distribution of variable, I think it's not too bad to understand. For instance, I have age distribution over here. I observe maybe a large sample or maybe even a population, right? And I realize a distribution for age between 20 to 30 is 23%, and 30 to 40 is 30%. So I get a kind of like a percentage distribution or relative frequency distribution for this particular variable. Now, I guess this is common sense now, right? So if I ask you, if I randomly pick a person, right, from this population, how likely this person's age is between 20 to 30? I guess it's pretty easy, right? If I ask you how likely this person's for 20 and 30, that's really this number, right? That's probably what you would guess, okay? That's a percentage of people in that range, right? So if you have that proportion of people in that range, the likelihood that you pick a person that is from that range is about that percentage, okay? And we call that relative frequency, right? But that number should be pretty close to probability too. It depends on what question you are dealing with. If you're dealing with probability, right, that's the likelihood of a subject being from that distribution. So hopefully you see that relative frequency is closely tied to probability, right? So a lot of time the mathematicians, statistician, they develop some mathematical model that actually help to model probability, but oftentimes those models are also good in modeling the percentage distribution, right? For instance, the distribution I believe most of you do know about, that is that bell-shaped normal distribution, right? Mathematicians come up with a Gaussian function, right, or or a distribution function that can help us to model or categorize or estimate the distribution that is of a bell shape. Okay, so people use that probability distribution sometimes to actually approximate the percent distribution of the population. Right? So hopefully you can make the connection between the relative frequency and probability distribution. Right? In chapter, I think, probably 6 and 7, right? Chapter 7 mostly talk about different type of distribution. They are discrete type, they are continuous type, right? The continuous type, the book actually talked about normal distribution because that's a distribution you've seen more often, right? In the beginning, introductory statistic, right? People realize a lot of quantitative variables follow that pattern. Right? So mathematicians come up with that Gaussian or normal distribution probability density function, and we can make use of that distribution function or probability density function to help us to model this type of variable, and then maybe able to use that to develop some kind of technique that we can do inferential study. Okay, so, but there are other type of variables. So there's so many different distribution model, right? Not just normal, right? You have sometimes distribution that is skewed to one side. For instance, in last class we talked about skewed to the right, right? So there are so-called exponential distribution that actually, so mathematically there's actually a function, right, that can help us to model those type of data skewed to the right or even skewed to the left. Okay, so there's so many distribution functions. If you use keyword to search on internet, you can find out like continuous or quantitative variable distribution function for those. You can see a long list of different distribution, right? But normal is a commonly seen distribution. And there are also other type of distribution like for discrete data, right? A lot of time in public health we deal with counting, right? Counting number of people have certain type of disease, right? And the counting number is discrete, so the counting number may have certain probability model, and actually mathematically people did develop some model. One of the model that often seen is so-called the Poisson Distribution. Okay, so in chapter 7, I believe it's chapter 7, right? If it's not in book, in my lecture note also mentioned that Poisson Distribution, right, is a probability model modeling the probability distribution for those counting numbers. Okay, and also when we do sampling in public health, right, we try to take a sample and use that to understand in the whole population what proportion of people have disease, probably certain type of disease, or in favor of certain type of policy, right? You're taking a sample, the finite number of subjects, and you're interested in how many of them is in favor of policy 1 versus not in favor of policy 1. Those are counting number again, right? Those type of counting number, there's some kind of probability model can be used to model those type of situation. Commonly seen model is the binomial distribution model, which you will study also in that chapter. Right? So in that chapter there are several models. Right? So if you go to, actually we probably can go there very quickly. That probably is week 4. Or actually we can go to lecture video. Right? So while you're studying, and for each chapter, right, I think I always put a link to lecture video, which is a page, right, contains a recorded lecture video. I think I recorded a long time ago, maybe 8-9 years ago, right? And week 4, actually week 3, we talk about different type of distribution. So you see the things I mentioned, the binomial distribution, Poisson distribution, right? So and there are videos actually talk about normal distribution. Right? So you want to review all these different distributions. I've set up some exercise problem, quiz number 2, I think, right, that allow you to actually practice these ideas. Right? So in my lecture note, lecture video, I actually also mentioned method of counting. Right? I wonder if you remember the permutation and combination formulas. Right? In fact, the combination formula is used in modeling counting number, like from a binomial experiment, right? So it'd be good to know what is that combination formula like. And so the counting 1 and 2 talk about those counting counting techniques, right? It's not actually definitely necessary to go over this, but it would be good, all right, if you have spare time. It would be good to actually review these permutation and combination things, the basic idea of counting. Sometimes people use that actually to model the probability, right, for a random experiment. And in there, it talks about a combination formula, which is used in binomial experiment. Right? So hopefully you can go through these lecture notes, right? Especially the discrete and continuum. If you want to deal with probably distribution model, like these two in chapter 7, right? It talks about those different models. Okay. So the counting technique, if you like, you can skip. Right? It's really not crucial, except for knowing that combination formula. But if you don't know that combination formula, it's in the binomial model. If you know the idea of the factorial, right, you'll be able to calculate the probability. So it's not crucial, right? So if you don't have time, you don't really have to go through the counting technique. But you like to go through the basic idea of probability, understand the basic rules and probability. Okay. So what I like to do today is actually in the lecture, I like to review a couple of things. The idea is simple, but often students have trouble with it. It's the conditional probability. Okay, so we want to look at the conditional probability, do a quick review of conditional probability in today's lecture. Okay, so you probably, when you see these notation, you probably hate them, the mathematical notation, but that's mathematically the notation, how we define the conditional probability. So you have two events, for instance, right? The conditional probability event A to occur given that B has occurred. That's one way to define the conditional probability, A given B, right? So that's a chance of A to occur given that B has occurred. Right? That's one way to define conditional probability. Or we can say conditional probability A given B is that originally you have a sample space, right? Now, given that new space B, under this new condition B, how likely A can occur? That's another way to look at the conditional probability. And I drew the Venn diagram. Usually it's a good kind of diagram for people to understand different relation in different situation and probability problems. Right? So here, the big box is like the whole universal set, right? And B is an event, A is an event. Okay. So conditional probability A given B is the probability that B has occurred, right? And how likely A occur. So this circle, this disk represent the event A, and this circle it represent event B. Okay, and so there is an intersection between the two. For instance, in my lecture video, I use an example that A is a group of smoker, and B is a group of people who have cancer. Right. So among those cancer, some of them are smokers, some of them are non-smoker. Right? So we can look at the conditional probability A given B as if you look at those people who have cancer, how likely them smoke, right? Those people smoke. That's the idea of conditional probability. Right? So you have a whole population of people, but some of them have cancer. Right? So among those people who have cancer, what proportion of them are smoker? That's this conditional probability. And sometimes you have these proportions, right? This is the intersection of two events, A and B. People who are smoker and have cancer, right? B is the whole group of people who have cancer. So that proportion, right? The intersection of two events, those who are smoker and have cancer, out of all those smoker, right? That's a conditional probability of smoker given that a person have cancer. Okay. Sometimes the information provided is counting number. Right, you have number of people in here, and also out of all the people in this group of having cancer, the ratio of that can give you the conditional probability. Right? So the idea is not really hard, right? So if we look at this data that we looked at earlier, the age group, right, from 20 to 70, and we group them into 5 categories, right? So totally 100% of people in the population. But if our question is this, among those who are 40 and older, right? So we're only interested in people who are 40 and older. So that's this group. What percentage of them are in their 60s? That means this group out of all, right? So this whole group above 40, that's the condition event. And the 60 and above, or in there 60, that's the event of interest. That would be like event A. Okay. So in this case, if we want to answer such a question, that pretty much does this 2% out of this overall, like 30 plus 10 plus 2%. The ratio of that is the condition probability, 4.26. So hopefully that makes sense to you, the idea of conditional probability, right? Originally, we have actually the whole population, but now we set a condition. We're only interested in those who are age over 40, right? So that's the condition event. Among those, how likely the person is in their 60? That's this 2% out of these, 47%. That's the idea of conditional probability here. Hope that makes sense, right? So, and in this situation, we're using actual percentage. The probabilities like percentages, as I mentioned a little bit earlier, right? So we can use a ratio of these probability, right, or percentage. This is actually the intersection of the two events. It's over 40 and it's in there 60. That's this 2, right? Over all the people that are in event B, that's right over 40. So that ratio. I think it's not too hard to understand, right? The next slide actually is using a graph to understand that situation. We're talking about this whole group of people among 40. What proportion of them is in here? That's the conditional probability of A given B. Those 60, right? People at age 60, out of those who are 40 or above. Okay, so so the idea is very simple, right? What's that conditional probability there? That's a good example of conditional probability. So this intersection of A and B pretty much is this just 60, right? And out of this B, which is everything that is 40 or above, that's the group of our interest. Although originally we have a population that's from 20 to 70 age, but now we're only interested in those who are 40. Among those 40 or above, right, what proportion that is in 60s? And that's the conditional probability of in 60, given that they're 40 or above. Okay, and this is actually based on the count. Sometimes the information you get is just the frequency, not the relative frequency, right? Then you can use the ratio of these counts to get that conditional probability. Okay, hope that makes sense. The idea of conditional probability is pretty simple, right? And I mentioned the term relative risk. Right? The relative risk is a useful statistic that people use it to assess or to use it to show, to present the seriousness of a risk factor. Okay, so relative risk is actually defined using a ratio of two conditional probability. For instance, if you recall this example that I mentioned in our last lecture last time, right? Last Saturday, we have two type of treatment, two level of treatment. And treatment A using this amount of dosage, and then the amount we have 100 people involved in that group. 44 have hypertension out of the 100. All right. So we get the conditional probability of having hypertension among those who took treatment A. Right. So that's a conditional probability of having hypertension given that it's taking treatment A. Then we can have a probability of having hypertension given treatment B, right? That's 29 out of 100. Okay. So relative risk of having hypertension for treatment A group versus treatment B will be what? The ratio of these two conditional probability, right? 44 out of 100 versus 29 out of 100. Right? So this 44 out of 100 actually is conditional probability of having hypertension given using treatment A. Right? And then 20 out of 100 is actually another conditional probability. So the relative risk is actually defined by the ratio of two conditional probability. So in this case, we have 1.52 if you take this ratio. So this tells us if you take treatment A, right, your risk of having hypertension is about 1.52 times than taking treatment B. Okay, but you have to be careful now, right? What type of study is this? If this study is a cohort study, it's an experimental study, then this would make sense, right? If this study is observational, then this number is questionable, right? Remember last time we talked about this, right? There may be some confounders in there, so you probably have to make some adjustment to it. Okay, but anyway, if I assume this is from an experimental study, right, we properly control all these possible confounders, right? We do randomization. Then this result actually tells us treatment A is probably better than treatment, worse than treatment B. You have higher risk of having hypertension, right? And again, this is giving you an idea, right, how relative risk is defined, right? It's actually based on the ratio of two conditional probabilities. So here I kind of try to give you the formula for it, right? I use A, B, C, D to denote the frequency, right? So this is a kind of contingency table, and we have a column variable, outcome variable. That first one is disease, second column is no disease. And we have a risk factor. The first one is exposed to the risk factor, and second one is not exposed to the risk factor. So we have these frequency distributions. So A plus B is total number of people who were exposed. C plus D is total number of people who are not exposed. Okay. Now, if we wish to figure out the probability, conditional probability of having disease, given that you're exposed to the risk factor, that's A over A plus B, right? So that's a conditional probability of having disease giving exposed. And then the conditional probability of having disease giving non-exposed is what? The C over C plus D, right? So we know these conditional probability. So what is the relative risk for having disease given that you're exposed to the risk factor versus not exposed? That would be the ratio of these two, right? So relative risk will be defined by the ratio of these two conditional probability. Okay. I hope that makes sense. All right. So here we have another situation. I use this in a lot of my classes, different classes. This is examining the smoking as a risk factor, and then outcome is what having cancer or not. Okay. So again, this is actually from an experimental study, which is not likely to happen, right? But if it is, right, then this could be on the rats or on the mouse, right, mice. So we have 50 subjects exposed to smoking environment. 20 of them have cancer. Another 50 subjects not exposed to risk, this risk factor, not exposed to smoking environment. Then we have 5 have cancer out of the 50. So if we want to study the relative risk of smoking, right, in giving cancer, then if we use this the frequency information, then the conditional probability of getting cancer for smoker or smoking subject or subject exposed to smoking environment, that's just 20 out of the total 50 in that group, right? And likewise for the cancer rate for non-smoker is 5 out of the 50, and you get 0.1, right? So the ratio of these two is the relative risk. Likewise, this is using the frequency information. Sometimes and oftentimes people report the relative frequency information percentage. So out of all, we have 20% in this group, cancer and smoke, 30% smoking and no cancer, 5% non-smoking and have cancer, 45% non-smoking and no cancer. Right? We can also find these conditional probability. Right? Conditional probability of cancer giving smoker, that's this 20% out of this 50% in this overall percentage, right, in this data. And so that's 0.2 over 0.5. The conditional probability of cancer given non-smoker is just 0.5 over 0.05 over 0.5. So we get the same number, right? The difference between this one and previous example is this one used a relative frequency and early one used a frequency. Right? So the ratio again of these two is 4, right? 0.4 over 0.1, so that's 4. So that's the relative risk, okay? So if the study is experimental, okay, then we can conclude that if you smoke, your risk of getting cancer, right, is 4 times than those who were not exposed to the smoking environment. Right? So that's the idea of relative risk. Okay, it's pretty simple if you understand the concept of conditional probability. It's defined by the ratio to conditional probability. Okay. Any questions? I think it's not too hard. Okay, and the other statistic that we use to assess or to evaluate the risk is the odds ratio, right? So the odds ratio, of course, is the ratio of odds, right? So first we want to review the idea of odds. What is the idea of what's odds, right? And in the disease and risk factor situation, right? Of course, the odds we're interested in, the odds of getting disease, right? So if you're exposed to risk factor, what is the odds for getting disease? That is defined also by a ratio of conditional probability. It'll be the conditional probability of, for instance, the exposed group, right? The odds of getting disease is the probability of getting disease versus the probability of not getting disease in the exposed group. So the probability of getting disease is A over A plus B, right? If A, B, C, D, again, is the counts, right? And then B over A plus B is a probability, conditional probability of not getting disease given you're exposed. So the ratio of these two probabilities, right? Giving you're exposed, you have disease versus giving you're exposed, you're not having disease, ratio of that is the definition of odds of getting disease if you're exposed to a risk factor. And the same thing, right, for the unexposed group, the probability, the condition probability of getting disease versus not getting disease, ratio of these two give you the odds of getting disease given you're not exposed. Once you figure out these two odds, the ratio of these two odds is the odds ratio, right? And of course, it can be simplified since you have A plus B on both of the denominator of these two odds, two condition probability. So the A plus B and A plus B cancel, right? Same thing, denominator, both have the C plus D as denominator for each of the condition probability. The C plus D cancel, you end up getting a number like this. Of course, this can be simplified to A times D divided by B times C, right? But I guess you understand the idea. So that's how we define the so-called odds ratio. Right? Now, the difference between odds ratio and relative risk, I guess you understand that, right? The odds ratio is based on ratio of odds, right? So it's conditional probability of a disease and non-disease that give you the odds, right? So you see the calculation of odds ratio and relative risk are quite different. When we interpret the relative risk, we can say that, for instance, in this case, we can say that the risk of treatment A to have disease is about 1.52 times than the risk of treatment B to have disease. Right? That's when we interpret the relative risk because it's a ratio of two probability. If you're doing odds ratio, the odds of getting disease for treatment A versus the odds of getting disease for treatment B, if you use the odds, then you cannot say that, well, the risk of having disease given from treatment A is 1.5 times. But this is odds ratio. You're not going to say that the risk, the chance of treatment A to get disease is 1.52 times than the risk or the chance of treatment B to have disease because those are not chance. Relative risk is, yes? Have a question? Okay. Probably just you turn on the microphone, right? Okay. So when you deal with the odds ratio, it's a ratio of odds, right? So ratio of odds is not ratio of probability. So when you try to interpret the result from odds ratio, right, whatever that number is, you're going to say the odds of getting disease for the exposed group is this many times than the odds of higher than the odds of unexposed group to have disease. So you want to use the term odds. Odds is different from probability. The same set of number, if you calculate relative risk, right, and calculate odds ratio, it may be quite different from each other. And why we want to use the odds ratio and sometimes we want to use relative risk? Well, as I said earlier, relative risk is used for experimental type of study. If you do really use the study really observational, right, that relative risk measure is really not a good idea. There are a lot of bias in there, right, because of those possible confounders. So oftentimes what people do is use the odds ratio to report the outcome. So let's look at this example here. The same cancer and smoking. This is more realistic, right? Usually, this is testing study on human subject, you won't conduct the experiment, so you can only calculate the odds, right? So in that situation, should we? To calculate odds, I shouldn't do this, right? But anyway, you have this conditional probability of given a condition, that's okay, right? Given a condition of smoke, the chance of getting cancer, right, for smoking group is 0.4. And the same condition for non-cancer is 0.6, right? So the odds of getting cancer if you smoke is ratio of these two conditional probability, right? That's actually 2/3. Okay. Likewise, you can calculate odds of getting cancer if you're not smoke. That's 0.05 divided by 0.5 over 0.45 divided by 0.5. So the ratio of that, this is how it's calculated, right? Odds of cancer for smoker is 2/3. Odds of cancer for non-smoker is 1/9. It's a ratio of two conditional probability to get the odds. Right? So the odds ratio of getting cancer for smoker versus non-smoker will be the ratio of these two numbers. Should be 6, right? The same data, if you calculate relative risk, that's 4. But if you calculate odds ratio, that's 6. So you notice that the difference is big, okay? So be careful, right? So when you're interpreting the odds ratio, you don't want to do the same thing as the way you interpret the relative risk. You don't want to say that the chance of getting disease for smoker, right, is 6 times higher than the chance for non-smoker. It's not 6 times. The odds is 6 times, but not chance. When we talk about chance, that usually we mean probability. Right? So, or you say, sometimes we'll say, well, since the odds ratio is 6, so if you smoke, you're 6 times more likely, right, than a non-smoker to have disease. That's a wrong statement. You say 6 times more likely, that means what? You're using probability. But here we are not using probability. We're using odds. So the way you can only conclude is that the odds ratio is 6, right? That means the odds of smoker to have disease is 6 times than the odds of non-smoker to have disease. Or you can say, well, based on this number, the smoker are more likely to have cancer than non-smoker. You don't want to say 6 times again, right? Only if you use a term odds, right? Then you can say, oh, the odds is 6 times. Don't say the likelihood or the chance is 6 times. Okay, so that's very important. Oftentimes people interpret it in the wrong way. Okay. So in this treatment situation, right, the odds of using treatment A to get hypertension versus odds of treatment B to get hypertension, right? If you look at this, I agree using A over B divided by C over D using the counts, right? So remember the denominator all cancel out, right? So I get the odds of 1.92. Remember that earlier when you do the relative risk, it's 1.5, right? Now it's 1.92. So the odds, again, odds ratio are different from relative risk. Okay. Odds ratio and relative risk will be very close when you have a situation, a disease is rare, which means what? The yes column are relatively much smaller than no column. If that's a situation, the odds ratio and relative risk to measure will be very close. So when you try to interpret the odds ratio, you probably can say that one is this many. If you're exposed to risk factor, you're about this many times more likely to get disease than the other one. Okay. But still, I recommend anytime if you're looking at odds ratio, try not to use the term like this many times more likely. Don't use that, right? Just say it's more likely, right? Or say the odds is this many times than the odds for the other category. Okay. Okay, any questions? The concept is very simple and it's very useful, right, for these type of statistics in public health research. So that's about the odds ratio and relative risk when we apply conditional probability to it. There's another thing that is commonly seen, that is the Bayes theorem, right? Which also uses the conditional probability. Now, in medical research or medical study, or even in treating patients, right, you see this happen often, right? You have a patient go to test for HIV, for instance. If if this guy tested positive, does it mean that this guy really have HIV? Well, the device sometimes has issues, not 100% correct, right? So it may likely that this person doesn't have the disease, but it was tested positive. Right? So issues like this, sometimes we can use a conditional probability to evaluate them. So that's what this Bayes theorem is about, and Bayes theorem is related to conditional probability. So let's look at this example. It's based on a study in 1979, right? People try to use this data, coronary artery disease, right? Data from 1,465 patients, right, to study this sensitivity and specificity of a test, okay, or apply Bayes theorem to study so-called predictive value of positive tests, right? So when a person actually is tested positive, really how likely this person is positive, and that's really important, right? So doctor will use that to make decision, or at least decide whether the patient is likely to have certain disease or really need certain type of treatment. So if we look at this data, right, there are totally 1,023 people actually have disease, right, and 442 did not have disease. But then if we use certain medical device to test, right, these persons, we find out that actually 933 of them tested positive, 535 of them tested negative. So there's something wrong, right? Totally 1,023 have disease, but 930 tested positive. In fact, among them, 815 really had the disease and test positive. So there are 208 people who had disease and didn't test positive, tested negative. So we often have situations like this when we're doing these testing, medical testing. So, and likewise, this column is like if you didn't have disease, there's a chance that you're tested positive, but there is possibility it takes negative. So this diagonal represents the correct decision, but this diagonal represents a not correct decision. Right? And there is a term that people, a lot of times medical doctor interested as a predictive value of positive test. That is really, if a person tested positive, how likely this person have the disease. Right? So that's actually a simple conditional probability. If we look at this table, it's easy to figure out because in this table, everything is spit out, right? It's showing there, right? So if we're interested in predictive value of positive test, which is a probability of having disease, given that a person have a positive test, which means that tested positive. So if you're tested positive, how likely a person have disease? That's that conditional probability. If you're tested positive, that's a condition, right? How likely a person have positive. So that's 815 out of the 900. Of course, in most of the situations, we like this number to be high. If this number is high, then you're more confident about the test result. And there is a term called prevalence, right? Of course, that's a percentage of people that have disease in this population, right? So in actually this test population, we have 1,465. Among them, 1023 have disease, so prevalence about 70%. Right? So that's a terminology, right? We use when we're doing this so-called predictive value of positive test. Now, this is one way to calculate the predictive value of positive test. When we have this complete information about this evaluation of this particular test procedure. But in practice, sometimes you don't have all these information. In that case, this prevalence, right, oftentimes is important while we try to calculate this predictive value of positive test. So at this point, let's just remember this term, right? Predictive value of positive test. That's really just the probability of any disease is giving that as test positive, right? Later on, we're going to look at another set of formula that we're giving sensitivity and specificity on. Right? So usually, medical doctor probably know these information. It comes with these tests, right? Or test service. Okay. So Sometimes if the predictive value of positive tests is not pretty high, right, you have a patient went through some certain tests, you find out that this person tested positive, but because of the predictive value of positive tests is not really so high, so you may want to suggest another test, right, to confirm whether this person whether actually have certain disease or not. Then follow with treatment. There are two other terms that are used for. One is sensitivity, and that's again a conditional probability. What is sensitivity? That's probably a person tests positive, given that this person have disease. So if a person have disease, how likely is this person will be tested positive? A lot of time when people divide these labs or these devices, they will provide these information, sensitivity and specificity. Sensitivity is given that person have disease, how likely it tests positive. So for this situation, with this data, the sensitivity is 80%. Right? That's among those who have disease, how likely it's positive. And the specificity is look at it as a non-disease one. Right? Those who don't have disease, how likely it would test it negative. That would be this 327 out of this 4. What I did here is using the conditional probability, but you know that that total denominator cancels, so it actually is just the ratio of these. So hopefully you understand the meaning of sensitivity and specificity. It's probably a people testing negative, given that person who don't have disease, specificity. Probably of testing positive, given person do have disease. And the predictive value of positive test really just reversing these two, right? If you're tested positive, how likely you have disease? Right? If you go back to that slide. If you tested positive, how likely you have disease? And oftentimes you'll provide a sensitivity and specificity, and then you like to understand and get a sense what's the predictive value of positive tests, right? And you can use those two values to compute this predictive value of positive tests. So anyway, let's look at that. The idea is so-called Bayes theorem. Okay, so suppose you have a certain medical device, right? You use it to test certain type of disease, and you're dealing with certain population that the disease prevalence is 20%. So D plus means the probability or percentage of have disease, and D minus means no disease. So we know that 20% of people who have disease and 80% of people who don't have disease, right, during going through the testing. And information also given, that is specificity, that is what? 98% here is a specificity. That's out of these, 98% will test negative. Among those who are negative, don't have disease, 98% will test positive. And that measure is the so-called specificity. Out of those who have disease, we say 99% tested positive. Right? Negative will be specificity, right? Out of those who don't have disease. But for those who have disease tested positive, that's so-called sensitivity. Now, under such a situation, if a person is tested positive, what's the probability that this person has a disease? How do we do this problem? There are different approaches to solve this problem. Those who learn the basic counting or the basic tree diagram in study probably, they can develop a tree to solve this problem and to answer this conditional probability question. Right? If you are tested positive, how likely you get the disease? Based on the conditional probability formula, actually, you should find the probability of tested positive and have disease over the probability of tested positive. That's the definition of conditional probability. And we can get these numbers from a tree diagram. Well, the idea of tree diagram is this. Right now, we have a population, right, a group of people of interest. Some of them don't have disease, some of them have disease. But then, among those who don't have disease, some of them tested positive, and some of them test negative. Among those who have disease, some of them test positive, some of them test negative. So, if we're interested in people who have disease or not, versus whether the person will be tested positive or not, we have all these four possible situations. Overall, we have all these four possible situations. Okay. So you have either this event happen or this event to happen and so forth. We have these four possible situations. Now we know the probability of having disease or not. We know that's actually 20 and 80%. We also know some of these conditional probability, right? So there is so-called the multiplication rule. If you look at this formula here, right? If you're interested in finding these two probability of this event, it's the product of these two. So this is something I actually so-called the multiplication rule. While you're reviewing this probability chapter, you will get that. Right? For any two events, right, the probability of event, one event and another event occur, right? This probability can be calculated by this paired conditional probability, which means all these probably can be calculated, right? This probability of D minus and a T plus, that means probability of no disease and tested positive, can be figured out by multiply these two numbers. If you look at this formula, So if we get these numbers, 80% and 20%, right? We get these numbers too. The sense specificity, right, is the probability of testing negative given people who don't have disease, right? Then, of course, if it's 98%, the probability of tested positive if people don't have disease is 20%. This is complement of it. Also, the sensitivity. This is specificity. The sensitivity is of what? Given you have disease, tested positive. It's given, right, from this test. That's 99%. Then the probability of having disease, given that you have disease that you were tested positive 1%. That's the complement of that. And in fact, these two information you don't really need. You really need these two information. And these pair, these two numbers multiplied together, you get this probability. These two numbers multiplied together, you get this probability. What is this? This is if you're tested positive, or a probability of tested positive and don't have disease. I think it makes sense, right? How do we get this probability? This is probably of a person who don't have randomly select person who don't have disease and tested positive. How can you get that number? Here we have probability of people who don't have disease, or percentage of people who don't have disease, that's 80%. Then we say among those who don't have disease, your tested positive is 2%. Okay? So if you want to figure out overall what percent of people who don't have disease and tested positive, that's this 2% out of this 80%. Right? I hope it's making sense. Right? So the product of these two can give you the probability of a person who don't have disease and tested positive. Same thing here. If you want to find out the probability of a person who have disease and tested positive, here you have the probability of people who have disease that is 20%. We say among those, 99% were tested positive. So if you want to figure out the probability of those people, percent of people, right, probability of percentage is the same thing, right? Percent of people who have disease and tested positive, that's really this 99% out of the 20%. So multiply these two together, you get this one. Okay. So among all those four exams, you have no disease tested positive, no disease tested negative, and have disease tested positive, have disease tested negative. And you like to use these probably. In fact, all these can be calculated, right? But your goal is to figure out, given that tested positive, how likely you have disease. And that's ratio of these two conditional probability. Not conditional probability, but these two probability. This is probably a joint event. A probability of have disease and positive. That's this number. Okay. Divide by the probability of tested positive. Now, or percentage of tested positive. Out of these four outcomes, only the first one and third one about tested positive. So adding them together, that you get the probability of tested positive or percentage of tested positive. So you get all the information now, right? In order to get this probability, predictive value of positive test, you just use this number divided by the sum of these two, right? This number is on the numerator, sum of these two in the denominator. You can get the probability. So to solve this problem, that's how you do it, right? Use this number, divide by the total of these two. You get the probability that's 0.925. So that tells you the predictive value of positive tests for this particular test, right? is 92.5%. That's pretty high. Okay, that's a high level. So, but because the sensitivity and specificity of these two tests are pretty high too, right? The test itself performed pretty well. So that's what Bayes' theorem is about. It's actually a special conditional probability. Given that you have this type of conditional probability, right? You know disease, given disease, and figure out whether it's tested positive or not. You can find out the conditional probability of giving tested positive, whether you can find the probability having disease or not. That's Bayes' theorem. Let's look at another example, right? So this is one way to solve the problem, right? Now, if you do that problem, you actually realize that that same formula, right, can be written in this form. I think my, well, actually, that's fine, right? That formula can be written in this form. This thing on the numerator is actually is this number here, right? If we go back to this formula, the predicted value of positive test is conditional probability of having disease given tested positive, right? And that conditional probability is either can be written in this form or written in this form. Okay. This is a probability of having disease and given tested positive. And that number is what? That number can be figured out by multiply these two numbers. What about this number? This number is the same as this. That's a product of these two numbers. What about this number here? Probability of no disease and tested positive. That's a product of these two numbers. So in fact, the whole formula, predicted value of positive test, can be written in this form, and this form can be also, you can fill in more detail about these numbers, which is the pair of these, product of pairs of these numbers in there. So that gives you another set of formula like this, right? Actually, it should be like this, right? Actually, in the lecture springboard page, actually, I have another formula for this, right? But anyway, let's look at this question first, right? How we use the idea we just learned there to figure out the predicted value of positive test. Right? Suppose that, look at this question. Suppose that 84% of hypertension and 84% of the population is of hypertension, or we have 80% hypertensive out of the population, and 23% of normotensive, right, and are classified as hypertension, right? So this number actually tells us that well, what is the specificity? Right? 1 minus that is specificity. Okay. And if it is estimated that the prevalence of hypertension is 20%, what is the predicted value of positive test? So over here, we have 84% of hypertension and 23% of normotensive that are classified as hypertension, right? So 84% is the sensitivity, and we have 1 minus this is the specificity. Okay, so kind of these two numbers kind of help us to understand the sensitivity and specificity. Okay. It said if it is estimated that the prevalence of hypertension is 20%, what is prevalence? Right, that is this D plus. And in that question is 20% the same thing. What is the predicted value of positive test? So that's the same question there, right? So we want to figure out predicted value of positive test. The numerator is the product, is actually this value, probability of having disease time tested positive. That would be this so-called sensitivity times the 0.2, right? If you refer back to the previous problem, right, that's a probability of having disease times the probability of tested positive given having disease. So that number with the sensitivity given, right, you can multiply it with prevalence to get the probability of tested positive and having disease. So these two numbers should be the same. Probability of tested positive and don't have disease. That's actually, if you go back to this table, that's really the product of these two numbers. That's a percentage of no disease, percentage of have disease, 20% percent of no disease, 80%, time the actually the if you're tested negative, if you don't have disease and tested positive, which is actually the component of the specificity. So if you look at this, that's really that 23%, right? So you have that product. So this example is just telling you if sensitivity is given and specificity is given, right? Of course, this is not specificity. If you're given specificity that is 77%, you should be able to figure out 23% right away and be put in here. Then you get the predictive value of positive test, that is 48%. Okay, so a test that has 84% sensitivity and 77% specificity with a prevalence of 20%, the predictive value of positive test is pretty low. It's like 48%. And that is not good, all right? If you're tested positive, the likelihood you have disease is only 48%. That means, well, you don't really have a clue, right, whether this person has disease or not. And predictive value of negative tests would be similar, right? It's just if you're testing negative, how likely you don't have disease. You will go through similar process, right, to get this, except for you're going to deal with negative, T negative, and D negative, so positive. Right? Whenever there's a positive, you become negative. Right? And so if you look at this problem here, right, the actual prevalence 20%, you get 40% that is predictive value of positive. What if the prevalence is only 2%? In this question, if you look at this formula, I think this somewhat give you a formula now if you want to figure out predictive value of positive test, right? 84% is sensitivity, so the formula itself can be treated this way. So this is another approach when you do this predictive value of positive test calculation. If you have the sensitivity, if you have the prevalence, okay, you also have the specificity. If you have a specificity, find a complement of that, right? That'll be this number. And this 0.2 is what? Again, is the prevalence. So this is that sensitivity. And this number is what? Is 1 minus the prevalence, right? So the predictive value of positive test can be the sensitivity times the prevalence over, again, sensitivity times prevalence, plus the complement of the prevalence. That's 1 minus the prevalence, times the 1 minus specificity. Right? So that's another formula. If you are given, or you were provided sensitivity and specificity and also prevalence, if you have these three numbers, you'll be able to calculate the predictive value of positive test. Okay, I hope you see that. So what I want to say is, if you change this to 2%, the prevalence is small, right? If you try to calculate this again, you get a very small number. All right, let's try that. Right? Maybe pull out an Excel worksheet. Right? Quickly calculate this. I forgot what that number is, so we can quickly calculate this number. Let's see if I can make this bigger. So maybe I call this that is that 0.84 specificity. That is 77. We have prevalence. That's 20%. Here, the predictive value of positive test can be calculated this way. So I want to say predictive value of positive test. To calculate this, how do I do this? I guess most of you probably know Excel, right? I hope you do. So when you do Excel, you want to calculate something. You start with the equal sign. I remember what I want to do. Let me see. Let's have a look. You see the formula. So I want to have to show these numbers. It'll be the sensitivity times the prevalence. Right? I'm going to use the sensitivity times prevalence. Okay, and divide by the sensitivity times the prevalence plus 1 minus specificity times time 1 minus prevalence, right? That's what I said. So you get the formula like this. It's 47.7%, about 48%. Okay, so you can use Excel, but I can't remember whether I put a problem like that in your quiz or not, right? But anyway, so this tells you that if you have sensitivity, specificity, and prevalence, you'll be able to calculate predictive value of positive tests. I hope this example helps, right? And my question was, if, well, I think it is okay. If I change the prevalence to only 2%, what would that change the predictive value of positive tests? Oh my God, that's only like 7%. So predictive value of positive test is that low. That means if you're tested positive, the likelihood you get the disease is very low. So the prevalence is a very important number there too, right? Hope you see that. Okay. There is a term called diagnostic test, and there's a term called screening test. Let's say we're try to screen HIV. Say screening, that means that we try to do this test on the whole population. Try to screen to see who has it or who don't have it. And the diagnostic test means what? You see a doctor, and doctor look at the symptoms and all these things and summarize, and then think, well, you are pretty likely to have certain disease. So under that assumption, you were sent to do the diagnostic. So that's called diagnostic test. Right? Some people have an idea that you're very likely to have it, so you were sent to do the test. So for that kind of situation, you're doing diagnostic tests, your prevalence will be higher, right? I hope most of the physicians do a good job when they look at the patient's symptoms. They know, right? They have a high, the patient who's sent to do the test will have high probability of having disease. So usually when you do diagnostic tests, now this number will be high. I hope most physicians are doing a good job, right? So you have high prevalence while these patients are sent to go through for the testing. So assuming that 80% of people who send for the test do have the disease, right? If that's an assumption, you look at predictive value of positive test, it becomes high. Okay. If the doctor is not doing a good job, they just randomly send people to do the testing, so the rate probably will be low, right? Let's say 50%. Now the predictive value of positive test will be low. Okay, I hope you see that what's going on here. Okay, and so I think we have some students who are in medical school, right? So later on, you probably will take the step 1 exams and I see a question like this also in those steps, but probably not actually having you to do the computation. Some question probably actually having you to do the computation, right? To see if you have sensitivity this much, specificity this much, and then you have prevalence this much, then when you have patient, going through the test, would you use that test to make decision, or will you send the patient to do a second test to confirm? Oops, I'm sorry. Excuse me. 我现在在上课哈，等一下哈。Sorry, I have a phone. I thought I actually silenced it, but I didn't. Anyway, so anyway, where were we? Okay, so you understand that prevalence actually play an important role in the calculation of predictive value of tests. I hope this lecture actually helps. If you go to our lecture note 3, if you look at this week 3, there's a note here. If you click on that, you'll see this formula I just mentioned. All right, so that's another. I tried to show you. Usually, I try to show students how the tree diagram looks like. So, but if you want to use a particular formula that has sensitivity prevalence in there, and specificity in there, and want to calculate predictive tests, you can actually use this formula. But I hope you understand what's going on. This tree diagram can kind of help you to understand what's going on, how we develop this formula to do the computation of this predictive test. The idea over here is actually so-called Bayes' theorem. I guess most of you are probably more interested in using such a formula. Any questions? Do you have any questions? Anybody? If you don't have any question, I think it's 11, almost 45. I think we can stop here. Okay. So I guess most will be finished week 2 material. So I hope my lecture will help you a little bit on studying material in week 3, Bayes' theorem especially. So you can go over these material. These are all. Some of my lecture notes are real movie. I wonder if you have problem viewing it. You need to install a real player. Years ago, there was some difficulty, but I think they improved the software, so it's doing better now. Right? So try to install a real player to view some of these lecture videos. But like I said, most of you have studied all these materials. So what you can do is just click on these lecture material and go over it, right, to see whether there's anything that doesn't make sense to you. Then you can then go to the video. And I think I mentioned that next 2 weeks I'll be out of town, right? But I still have access to email. So if you have any question, feel free to shoot me an email, right, and ask me. Okay. Any question? So if no question, then I guess we're gonna stop it here. Okay. So hope you have a good weekend. Okay. So I'm gonna make this video available sometime this afternoon. So in case you need to go back. Okay. So that's it.